Alright, going to go over chapter 3 here, which deals with network protocols and communications. Some takeaways from chapter 3 are to explain how rules are used to facilitate communication, explain the role of protocols and standards, and explain how devices on a LAN access resources in a small to medium-sized business network. In any type of communication, whether it's humans or computers or devices communicating, we always have a few specific things. We have the message source, or the person communicating, or the computer that's communicating. We have the message destination, the person we're talking to, or the receiving device or computer. And then we have our signal. Maybe it's our spoken words, or maybe it's electrical pulses being sent across a wire with computers. And then we have our medium. Our medium would be that wire that we're using for the computer, or maybe it's the air for wireless, or maybe it's a quiet room for two people communicating back and forth. Whenever we're communicating, we always establish rules. We may do this explicitly, or it might just happen for us. We always identify a sender and receiver. This is pretty easy when two people are communicating. The sender is always the person talking, and the receiver is the person that's listening. Well, in a computer network, it's not quite that simple. So we have mechanisms that help us identify who's communicating and who's supposed to receive. We have an agreed method upon communicating. Is it going to be face-to-face? Are we going to talk on the telephone? Are we going to text? Are we going to send a letter? Are we going to do it through photographs? We definitely must do this as well when two computers or devices are communicating. We have to communicate with a common language and common grammar. If I'm going to talk to someone from another country, I need to make sure that they also speak English. If I don't speak another language that they speak, then the communication is going to break down. So we must have common language. The speed and timing of delivery, we can't have two people communicating at once. We can't have one person talking too fast. We have to make sure that the speed and the timing works out for both parties involved. And then confirmation or acknowledgement requirements. Many times when two people are communicating, we acknowledge each other by nodding our heads or saying yes, or maybe we ask the person to repeat themselves. But either way, we know whether or not they got what they needed and they heard what we were trying to communicate with them. This chapter talks about formatting messages and encapsulation. What I want you to know about encapsulation is that we're adding something to our message. Many times when computers communicate, we're adding addresses such as a MAC address or a TCP/IP address. Here they have you think about a letter. And when you address that letter, you start to add different things. You add who the recipient is, you add their address, you add who the sender was, probably yourself, and your address, you add a stamp, you add all these different things to comprise the whole letter. Message size. In a computer network, we want to always divide up our messages into different packets and frames. This might not work so well when two humans are communicating, but let's pretend you want to download a movie file. It would almost be impossible to take that entire movie file, download it in one chunk from one computer to the next, because it's just too large, too cumbersome to work with. If one little bit or something didn't make it, then the whole file would be corrupt. Think about sending a letter to one of your friends that's 100 pages long. What you would do is you would take every single page, put it up in its own individual envelope, and send it out. So you'd have 100 different envelopes, and the person you're sending it to would have 100 different pieces of mail that they would get. Now, like I said, that probably doesn't work very well for humans communicating, but that's essentially what we do when computers communicate, is we take the message, divide it up into multiple pieces, and then send it along the way. When we talk about computers and devices communicating, we're going to talk about three types of communication: a unicast, multicast, and a broadcast. Unicast is from one device to the next. So if I take this picture over here on the right hand side, I have this computer communicating directly with this computer. In human communication, be one-to-one. Multicast would be one to many. That would be like this computer here communicating with these two computers. So these two computers are the only ones listening, and this is the one communicating. This would be like in a classroom situation where I would go over and communicate with just one table. There's multiple tables in the room, but I'm communicating with just one table. Broadcast, this would be like the teacher communicating with the entire class. Essentially, you're kind of shouting out in the room. Or on a computer network, I always like to say the computer is shouting out on the network so that all devices hear it. In a broadcast situation here, this device would communicate with every single device that's connected to the switch. What a switch does when it receives a broadcast message is it floods it out every single port. And when it gets flooded out every single port, all devices get that message. So we talked about some different things that must happen during communication. Who the sender is, who the receiver is, how we're going to acknowledge, how fast we're going to send. All of these different things that happen in a computer network are governed by our protocol. Our protocol is our rule or our language, and it governs how the communication is going to take place. An example of a protocol is the HTTP protocol. We use this protocol to get web pages from a web server. That dictates how that's going to work. Another protocol is the FTP protocol, File Transfer Protocol. This is going to dictate all of our rules and how all the communication is going to happen when we download files. Protocols are going to dictate how the communication is going to work, how fast the communication is going to go, how we're going to handle errors, how we're going to handle retransmission, how we're going to handle acknowledgement, amongst other things. Many times protocols work hand in hand, or multiple protocols work at the same time. I talked about the HTTP protocol and using that to get web pages from a web server. Well, in the background, we're also using the TCP/IP protocol so that we can get addresses so we know who the destination and the sender are. So usually when we're talking about protocols, it's not just one specific protocol that's working at one time. It's usually a collaboration of multiple protocols. In order to be able to communicate on the internet, a device must have the TCP/IP protocol enabled and installed. The TCP/IP protocol is the most common protocol and is made up of a bunch of sub-protocols such as HTTP, FTP, DNS, SMTP. These are all part of the TCP/IP protocol suite. So most of the protocols that we will talk about, or actually all of the protocols we'll talk about in this class, are part of the TCP/IP protocol suite. That again you must have to be part of the internet. All the different protocols and communications that happen on a network are developed by some sort of standards organization. One that I'll use, for example, is the IEEE 802.11 standard. This is the standard for wireless. There's wireless A, B, G, and N, and all these different standards that are out there that are coming out. These different standards were developed by the IEEE, and they dictate how fast wireless communication can go, how far the wireless communication can go, how that wireless communication can work. So the point is that these protocols and these standards don't just come out of nowhere. There are actual organizations that take a look at these, come up with the best method, and that's what they say all wireless communication must adhere to. Some of the more popular ones that you may hear are the ISOC, the IAB, IETF, IEEE, and the ISO. There's also the EIA, TIA, the ITUT, the ICANN, and the IANA. I'm not going to get too involved with these different standards organizations in this class, but just know if you see like the EIA, TIA 568B standard that we'll talk about when we create patch cables, that means that was a standard developed and created by those specific groups, and if we want to make a patch cable, we must adhere to those specific standards. This chapter talks a lot about using a layered model to networking. There are many different benefits to using a layered model. It helps break network communication down. It helps foster competition and allows different vendors' devices to communicate with one another. For example, a 3-COM switch communicating with a Belkin network card, or a Cisco router communicating with a Juniper firewall. If all of these different vendors and brands came up with their own standards and their own methods of communicating, we couldn't have this interoperability with these different makes and models. Having a layered approach to networking allowed devices to perform just the function that they need to at their layer and not have to worry about the other layers. The most common layered approach or reference model is probably the OSI model, and this is what we'll spend most of the time on in this class. There are 7 different layers starting at the application down to the physical. One way that I used to use to remember it, taking the first letter of each layer, is all people seem to need data processing, or please do not throw sausage pizza away. That's one way in which you can use to help you remember the 7 different layers. Again, every single layer is in charge of their own function. That's all they perform. Once they perform their function, they pass it to another layer of the OSI model. I do have another video explaining how this process works. It'll probably make a little bit more sense after watching that. But for now, what I'd like you to know is the 7 layers of the OSI model and the form that the data is in, their protocol data unit at each layer. So when we're working at the physical layer, it deals with our wires and our signals being sent. The form of the data is in bits, either it's a 1 or it's a 0. When we're working at the data link layer, we're working with MAC addresses and we're working with a frame. We've encapsulated our bits into a frame by adding MAC addresses. When we're working at the network layer, we're working with packets. At the transport layer, we're working with segments. And at the upper layers, we're working with our whole of our data. There's another reference model out there as well, the TCP/IP reference model. This only has 4 layers, and you can see how they compare here. We won't spend a whole lot of time on the TCP/IP model, but again, it is very similar to the OSI model. And again, each layer performs its own function before sending it down to the other layer. I briefly talked about breaking up our messages into smaller parts. This is known as segmentation. I used the example of sending a 100-page letter to your friend, where you take every single page of the letter, put it in its own envelope, and send it along its way. Doing this on a data network is highly desirable because it has many benefits. We can interleave different conversations on the network. When you use your computer, you probably have multiple things going on at once. You may be surfing the web, downloading music, and checking your email. All these different conversations can be on the network at one time. This gives us increased reliability of network communications as well. We can resend any data that's not received instead of having to resend large chunks of data or the whole of the message if it wasn't received. We can just send the one packet or the one piece that was missed during the communication. Because we have all these pieces on the network, it does increase the level of complexity. We do have to address every single segment on the network. We do have to process those addresses to see whether or not it's intended for the device in which it was sent to. So there's a little bit more processing that takes place, so there's a little bit higher level of complexity. But in the end, the benefits outweigh the disadvantages. When we work our way down the OSI model, we're working with different protocol data units. Or essentially what we're doing is we're breaking up our data into different parts. At the very top, we have the whole of our data. Maybe this is an email message. When we break up that email message, we work with a segment. And the segment takes place at the transport layer. We then take that segment and add some network information at the network layer to form a packet. We then take the packet and add some data link information to form a frame. And then the frame gets broken up into our bits, our 1s and 0s at the physical layer. So depending on which layer of the OSI model that we are on, we may be working with a different form of the data. And we'll talk about each form of the data throughout this class and the semester. Anytime we take that data and break it up and add different pieces to it, this is known as encapsulation. You will see that term a lot. Some things that we encapsulate are MAC addresses, IP addresses, header and trailer information. Essentially, we're adding something to that segmented data so that we can deliver it to where it wants to go. So when the web server here would send to the web client, he's going to encapsulate data on there. He's going to encapsulate the IP address of the client and the source address of the web server here. He would also encapsulate MAC addresses of the web client and of the web server. So he's adding those pieces so that we can deliver it. When it gets received on the other end, if it got received by the web client, we would then do the de-encapsulation. The de-encapsulation is going to strip off those things. It's going to strip off the header and take a look at the MAC addresses to see if this is the right client. It's going to strip off the IP addresses to see if this was delivered to the correct destination. So we have encapsulation and de-encapsulation going on. I've talked about a few addresses such as IP addresses and our MAC addresses. IP addresses are known as network addresses. We have our source and destination, who we're coming from and where we're going to, and these will never change throughout our communication process. Then we have our data link addresses, which are known as our physical addresses or our MAC addresses. We have the source and the destination for this as well. These can and will change throughout the data communication process. Let's take a look at this example here. We have PC1 who wants to send down to the FTP server. We have the IP addresses of PC1. PC1 is 192.168.1.110. The IP address of the FTP server is 192.168.1.9. And then we have our MAC addresses, which here are represented by all A's and down here all C's. Now you would never see a MAC address that looks like this, but they are 12 hexadecimal digits in length. So when we segment the data that wants to be sent from PC1 to the FTP server, one of the first things that we do is we encapsulate it into a packet by adding the source address and the destination IP addresses. So the source is who it's coming from, 192.168.1.10, that's PC1, and who it's going to, 192.168.1.9. Now these addresses, as I said, will never change, and these addresses are used to send from one network to the next. We also add MAC addresses, and the MAC addresses are used to communicate within our local area network. The MAC addresses in this particular scenario are not going to change because they're located on the same local area network. So it's coming from PC1, which is all A's, and going to the FTP server, which is all C's. So we would see this in what's known as a frame. When we add the MAC addresses, we now have a frame. We've encapsulated that packet into the frame. In the previous slide, we built the frame and we added the MAC addresses. If a computer does not know what the MAC address is of a destination, it will send out what's known as an ARP request. We will talk more about ARP in detail when we get to the Ethernet chapter. But essentially what an ARP request is a shout out on the network asking a particular computer with a specific IP address what their MAC address is. So the ARP request might say, hey computer 192.168.1.111, what is your MAC address? And then this PC would reply. If we want to communicate outside of our network, we must have a default gateway. Without a default gateway, we cannot communicate outside of our local area network. We still can communicate within our local area network, but not outside of it. If you were to go to your command prompt of your PC right now and type in ipconfig, you would see a default gateway. That is the address of the nearest router. That nearest router will be able to deliver that packet outside of the network if it needs to do so. So let's pretend, for example, that PC1 here wants to communicate with the web server. So when we encapsulate our data segment, the first thing we're going to add into it is our IP addresses. Source, who we're coming from, PC1, 192.168.1.110. 192.168.1.110. We're going to the web server at 172.16.199, 172.16.199. Again, these will never change throughout this communication process. What is going to change here is our MAC addresses. So at this point in time, we're going to come from PC1, which is all A's, and we want to go something outside of our network. So what we would do is we would send an ARP request, and we would say, hey computer 172.16.1.99, what is your MAC address? Well, this computer, the web server, is on a completely different network. So we would not get a response back from this web server. So instead, our default gateway notices that ARP request, and he says, hey, you're trying to get to a network that's outside of your local area network, so you need to go through me. So I'm going to have you send me that data so I can try to deliver it. So now the destination is all ones. So that packet's going to go from PC1 to the default gateway. Now the default gateway would send it from router 1 to router 2. What we would put inside of the frame now is the source. It would be coming from all ones, and then it would be going to R2. It would be going to the destination of all twos. So those would change, the IP addresses would not. Then when it leaves R2, the source would be all twos going to the destination of A, B, C, D, E, F, 1, 2, 3, 4, 5, 6. So again, those MAC addresses inside of the frame can change where the IP addresses do not. If we need to communicate outside of our network, we go through a default gateway, and that setting must be set up in the TCP/IP settings of your computer. There is a free tool known as Wireshark that's available for anybody to download on the internet. And what Wireshark does is it captures traffic as it's being sent on the network. It's a great tool to see these frames and these packets that we've been talking about in action. You can click on the frames that it sniffs on the network, and you can open them up to see all different sorts of information, such as the source IP address, destination IP address, source MAC address, destination MAC address, source port, and destination port. So we will use this program from time to time, and actually there's a lab in this chapter that walks you through how to set it up and use it, and I highly encourage you to go through that. That is all for this video on Chapter 3. Thanks for watching.